Hello, I'm Adrian Solis, and I'm a principal software engineer here at Microsoft Teams.
I'm Nick Bollier, another software engineer here at Microsoft Teams.
We're doing a two-part session on common yet surprisingly tricky scenarios for apps inside Teams. First, I'll cover authentication and authorization. I'll dive into tab single sign-on, which is one of our top feature asks, and I'm so glad that it's finally here. Then, I'll hand it over to Nick, where he'll go over two key challenges with proactive messaging. First is figuring out where to send a message, and then second is how to deal with throttling. Let's begin with bots and messaging extensions. For the common case where all you need is the identity of who was messaging you, note that the incoming request already contains basic information about the user. Once you've validated that the request is coming from the Microsoft bot framework, you can rely on the information inside the payload, like a tenant ID, username, user ID, object ID, that's already in the message. So, for example, let's say you wanted to restrict access to your bot so that it's only usable from within your org, then you can add middleware that drops all messages except those with your org's tenant ID. Now, things get more interesting when the bot wants to access other APIs. Say your bot wants to access the user's profile from Graph, or it may want to search things in SharePoint, or let's say it wants to read and write tasks from within Planner. Now, the standard way to do this is with a protocol called OAuth. And through that, users can grant access to resources without having to give up their username and password. Instead, what happens is the bot gets a string, it's called a token, and then it gives it to the downstream API so that it can act on the user's behalf. So when the bot needs a token and it doesn't have one yet, then it prompts the user to sign in by sending them a card that contains a sign in action. Clicking on this button will open the pop up window where the authentication flow runs. And at the end of that, the auth flow calls notify success with some state data. Now, Teams will send that data back to the bot so that it can kind of close the loop, let's say, and associate the result of the auth flow with the user that clicked on the button. Now, let's see what this looks like inside Teams. Here I have Expert Finder, which is one of our ready to deploy app templates. Now, one of its features is viewing and editing your profile inside Azure Active Directory. And to do that, it needs to connect to Microsoft Graph. Now, my demo user hasn't used Finder before, so when I click on my profile, the bot sends me a card asking me to sign in. And clicking on that launches the pop up where I can grant it permissions, the ones that it's requesting. In this case, since it's reading and updating my profile, that's what it asks for. And when I grant that, the pop up will close and Teams will send a message to the bot, which allows it to get a token. And then here you can see that it shows me my profile. Expert Finder was registered using Azure, so it was easy to implement the auth flow. It was able to use the Azure bot service, which implements key parts of the process for you. So instead of handcrafting the auth URL and what happens inside the pop-up window, we could simply send a sign-in action that points to a page that's hosted by the Azure bot service itself. Now it implements authentication and authorization, and then links the access token to the user that clicked on the sign-in button. And when we need the token again later, we can simply ask the service for the user's token. For providers that support refreshing access tokens, the service even takes care of that, and you'll always get a valid access token when you ask for one. This is exposed through methods in the Bot Framework SDK, through methods that are on the Bot Framework adapter. The SDK will even wrap this up in a pretty nifty OAuth prompt class that works really well if you're building your bot using dialogues. Let's take a look at the configuration and code for Expert Finder. Here's the configuration of the bot inside the Azure portal. Now, this can be a web app bot or a bot channel's registration resource. They both work. In the Settings tab, I added a new OAuth connection. In this case, I called it Expert Finder Auth. These settings for the connection have the information that are needed for it to complete the OAuth flow. And so for Azure AD, that would be the client ID, the client secret, the tenant ID, and the scopes that we need. As I said earlier, Expert Finder reads and writes the user's profile. So here we are asking for user.readWrite. Over in the bot code, I started by registering an OAuth prompt dialog. Now that takes the connection name from bot settings, the one that we created earlier, and then text for the sign-in card and the sign-in button. Then I just inserted that dialog into my waterfall, into the steps that my dialog takes, right before the step that needs the access token. And if you look at that, it's pretty simple. It can just get the token from the result of the previous step. It doesn't have to worry about talking to Azure AD or ensuring that the token is valid. Like the bot framework SDK did that for us. Now, this also works for messaging extensions because their auth flow is very similar to that of bots. There's just two main differences. So first is that instead of showing an auth sign-in button, what happens is that the messaging extension will return an auth response with a sign-in link. And then the user clicking on that link will open the pop-up dialog that we saw earlier. Second, when the pop-up closes, Teams will replay the original message, the original request, adding the result of the auth flow to that activity. And then the messaging extension uses that to get a token and then call the APIs that it needs to return results back to the user. Let's turn now to tabs and task modules, which are capabilities implemented as iframes inside Teams. Now, I want to start by emphasizing that the context properties that you get from the tab are just hints, and you should treat them as such. Although it's tempting to take the user's principal name, object ID, and tenant ID directly from the values in the context, remember that your code is running on the user's machine, and a malicious user can spoof these values and perhaps trick your tab into thinking there's someone else. So always authenticate the user before making decisions based on their identity. All right, so what does that look like? The auth flow for a tab is very similar to the pattern that we have for bots. The tab prompts the user to sign in by showing a button on the page. And then when the user clicks that button, it calls a method in the Teams SDK called authenticate to launch the flow inside the pop-up. At the end of the flow, the last page in the pop-up will call either notify success or notify failure to close the pop-up and send the result back to the waiting tab. Also, depending on their specific domains, the auth flow inside the pop-up and the tab may be allowed to share information by setting cookies or values inside local storage. Now, the next step towards a smoother authentication experience is what our documentation calls silent authentication. Now, this technique is really nothing more than just using an existing Azure AD session to get a token for the user. The ADAL and MStyle JavaScript libraries have a method called acquire token or acquire token silent that tries to get a token for a resource without needing the user to do anything. They do this by running an implicit grant flow inside the hidden child iframe. Now that works, provided one, that the user has already consented to the app accessing that resource, and two, that there's an active Azure AD session for the user. Now, when these conditions are not met, the tab has to fall back to the basic login flow that I showed you earlier. This is actually not uncommon. In the desktop and mobile clients, those clients use the native Azure AD libraries and they keep the auth session natively. They don't share that with Teams apps that are running as tabs. Now, that this is why you sometimes see apps that work seamlessly in the browser. They never ask for login, but once you use them inside the Teams desktop client or mobile, you'll see them prompt for login once in a while. Clearly, that's not ideal. So we've improved on this by introducing Tab SSO. This is a feature that it's currently in developer preview, but it will be generally available by the end of June 2020. With single sign-on or SSO, the tab calls the getAuth token method in the SDK to get a token for the current user. Now, this token is a user-delegated token for the resource that corresponds to your application. It's a signed token, signed JSON Web Token, signed by Microsoft, and so you can validate that on your server APIs. Your app can pass that to your API, validate the signature, and then use the claims in the token to validate and then verify the tenant ID, user object ID, and user principal name that you got inside the context. So that would be how you would do that securely. Now let's see what that looks like inside Teams. Let me show you what this looks like. Here's a simple app that gets a token through SSO. I'm using this tab for the first time, so when I load it, Teams shows me a dialog that says that the app needs additional permissions. When I click on Continue, Teams opens a pop-up and asks me for consent to sign in. This consent allows Teams to get an access token and send it to the tab content page, which in this case just displays the raw access token and the claims that the token has inside it. Let's look at the configuration and code that made that possible. Let's start with the configuration of the Azure AD app, which is inside the Azure portal. Under API permissions, I included several scopes. The first is OpenID, which is what lets the user sign into the app. Then I also added profile and email, which are two scopes that give the app access to basic information about the user, like their username and their email address. Then over here in the expose an API blade, I set the application URI to API : the domain of the tab, and then the application ID. In this case, I'm using ngrok to serve my tab from my local machine, and that's why the app URI that you see here includes my ngrok domain. Now on the same page, I added a new scope called access as user. And this is a scope that Teams will request when it gets a token for your tab. The description text that you see here is entirely up to you, but for consistency's sake, we do recommend that you use the standard text that we have inside our documentation. Still on the same blade, I added two authorized client applications. One is for the Teams desktop client and mobile client, and then the other is for the Teams web browser client. One last thing I want to point out is inside the manifest blade. Here, I wanted to include the access token. I wanted that to include the user's principal name or UPN. So I manually edited that to include the UPN inside the access token. Now in the Teams app manifest, I just added one section called Web Application Info and set the ID to the ID of the AAD app that I registered. And then I set the resource to the application URI of that AAD app. After all that configuration, the changes to the Teams tab itself is quite simple. I mean, after I initialized the Microsoft Teams SDK, I just called get auth token and passed it two callbacks, one for success and one for failure. Now, Teams takes care of the rest, prompting for for consent, like we saw. And then when it has the access token, it will call this callback and give it to the tab. Now that works well for authentication, which again, like in the bot case, sometimes that's all that you need. But if you need another API, if you need to call another API, say if your tab wants to get information from Microsoft Graph, you can actually use the token that you received through SSO to get access tokens to other APIs through a mechanism that's called the on behalf of flow. You'd send a request to the Microsoft Identity Platform with the user's token, your client ID and secret, and the desired scopes. And if the user has already granted your app those permissions, then you'll receive a new token back, and you can then use that token to call the API that you wanted, which is in this case Microsoft Graph. But note that in the current implementation of Tab SSO, the consent prompt only requests the minimum permissions needed to sign in the user. And that means that the token exchange that I mentioned earlier can fail, and you must be prepared to handle this error case. If you see a 400 bad request status with error codes of invalid grant or interaction required, you should relay that back to your front end. And then your tab can ask the user for further consent through the same basic tab login flow that we showed earlier. Alternatively, the tenant admin for your organization could consent to these scopes on behalf of all their users. And that works pretty well for custom apps that are published inside the org's app catalog. This code snippet from the tab that we saw earlier shows one way to do this. So here we see the exchange. This is the on behalf of flow. And since this can fail, I added a handler to the catch block that looks for the errors that I mentioned earlier, invalid grant and interaction required. And when it sees that, it returns a 403 forbidden status code back to the tab. The tab will then show the button to ask for more consent. Now, we've talked a lot about signing in users. Let's consider how to sign out. The most important rule to follow here is that if a user can sign in through a capability, your app must provide them a way to sign out using the same capability. Let me explain. If your tab asks the user to sign into your service, then that same tab must have a clear sign out button. Similarly, if the user has to sign into your bot to use it, then your bot should have a sign out command. And ideally, you would allow for spelling variants like sign out, like one word, or log out. You may even be fancy and use like NLP or Lewis to detect other phrases that equate to the user's intent to sign out of your application. And if you have a messaging extension that does auth, then that messaging extension should implement a settings page with a sign out button. This rule can easily cause your app to fail validation when you try to publish it to the App Store. So please pay attention to these requirements. Before I finish, I want to point you to the code that I showed in this video, Expert Finder, the app template, and the auth sample for the tab are available at the links on screen. You can download the code, please, and run it locally and see how you can apply these techniques to your own tabs and apps. Okay, thanks for your attention, and over to you, Nick.
Thanks, Adrian. Now let's look at another challenging topic in Teams, proactive messaging. First, what is a proactive message, and when do they get used? A proactive message is a message that is sent by a bot to start a conversation. This can be used for many things, such as sending an introductory message to users as an app, conducting organization-wide surveys or polls, and even sending notifications from external systems, like a service health monitor. Before we dive into the tips and tricks, let's take a quick tour of what can be done with proactive messaging. Here, we have the send message command, which allows us to send proactive messages right from the command line. First, let's try to send a message to ourselves. Don't worry too much about the parameters here. We'll get back to them shortly. Notice that I now have a new message from our proactive bot in both the activity feed and the one-on-one chat with the bot. You should also note the toast notification. These notifications work cross-platform and send push notifications on mobile devices. Now let's initiate a new group conversation by creating a channel thread. And look here, the app has initiated a new thread, just as instructed. Let's demo one last message to the same thread, just to show that we can. Now let's look at how this command is sending these messages. Here, you can see there's surprisingly little code required to send a proactive message using the Bot Builder SDK. Even more surprising is that it also highlights two of the fundamental challenges for proactive messaging. The first challenge is that we need these two parameters to know where to send the message. The second challenge is dealing with the unique throttling that affects proactive bots. These two challenges are the key topics we'll cover: getting the conversation coordinates and reliably sending proactive messages. Let's start by figuring out where to send the messages. To understand the conversation coordinates, it's helpful to look at something we already use. Here, we see an inbound message activity for a conversational bot. It has the usual fields for things like the type of activity, when it was sent, and who it is addressed to. But importantly, these two are responsible for indicating where the bot should reply. Let's call these two fields the conversation coordinates. The Bot Builder SDK helpfully manages sending replies to these conversation coordinates, and conversational bots rarely, if ever, need to use these fields. However, without an inbound activity, much of the effort of a proactive messaging bot is the discovery, storage, and retrieval of these coordinates. Before going too far, it is important to understand what controls each coordinate. The service URL changes between organizations, but every conversation within an organization will have the same service URL. The conversation ID is unique to each conversation, be it a one-on-one conversation with the bot or a thread in a channel. So we've already seen two types of conversations. The first is a channel thread that we saw the proactive bot can create and reply to. The second is a direct message to the user from the bot. Now, let's look at how we get the coordinates for these conversations. First, we'll look at how a proactive app can get the channel coordinates and use them to create a new thread. Then, we'll use this newly created thread to send additional proactive notifications to the channel. When a user installs the app into a team, Teams and Bot Framework send a conversation update activity notifying it of the installation. With the contents of this activity, the bot can then fetch a list of all the channels in that team. The IDs of these channels are the conversation IDs. To understand this flow, let's look at the contents of the conversation update activity. To start, let's identify how we know this is a team installation event. The first of these fields tells us this is our bot being installed. This ID is the application ID of the bot, prefixed with 28 colon. The last of these fields tells us that this is a team conversation. Now note that we already have the service URL for our organization. All that remains is to get the conversation IDs of the channels in this team. To do this, we'll use the team ID from the channel data to get the list of channels in this team. This code snippet shows us how this is implemented using the Bot Builder SDK. First, a connector client is constructed to communicate with Bot Framework using the service URL from our activity. Then, we use the team ID from the conversation update to get the list of channels for the team. The ID of each of those channels acts as the conversation ID. With these IDs and the service URL, the app now has enough information to create a new channel thread. Now, let's finish the flow and create a new conversation in one of these channels. Like before, we use a connector client to communicate with Bot Framework. Since we just made one, let's reuse it. The next section of code is forming the conversation parameters. These parameters tell Bot Framework where to create the new conversation. For this scenario, we want to create a new thread inside a channel. At the end, we see that we can get the conversation ID of the newly created thread. Combined with the service URL from the activity that started this message, we now have both conversation coordinates, which can be stored and used to send proactive messages later. The most used proactive scenarios are those which start one-on-one conversations with users. There are two ways to get the conversation coordinates for the unique conversation between the bot and the user: by capturing the conversation coordinates out of a conversation update, or by creating a new conversation between the user and the app. Let's start by looking at how to get the conversation coordinates from the conversation update. When a user installs a personal app, or has a personal app installed for them, a conversation update activity is sent, much like when the app is installed in a team. Looking first at how we know this is a personal install event, we can see one of the members added having the bot's 28 colon bot ID. What distinguishes this from a channel install event is that the conversation type is personal. Unlike channel conversation updates, however, the conversation coordinates for the user are right here in the activity. While the conversation update for personal installation is easy to use, it does rely on the app being installed for the user. Let's look at the way an app installed in a team can proactively message any member of that team. First, when the app is installed, the conversation update activity will be sent to the bot in the exact same flow we saw when getting conversation coordinates for channels. Now, instead of getting the list of channels, we can get the list of members. With this list, we can then create the one-on-one conversations for each member of the team. While that pattern works for existing members of the team, it is important to remember that the membership of a team changes over time. Thankfully, when a user is added to the team, Bot Framework sends a conversation update, which has the user's information to create the one-on-one conversation. Let's look at this flow in practice, using the Bot Builder SDK. Here, we can see the detection of both the location where this update is occurring and if this is an installation event. We check that the conversation is a channel conversation and if the bot was one of the added members. With that information, we can then use the connector client to get all the members of this team. After getting all the user members of the team, the bot then records this information. Now, let's look at the code that handles new users. In this block, we can see that the members in the incoming conversation update activity already have the information we need. So we just store it. Now, let's finally look at how to get the conversation coordinates from this information. In this snippet, we use the connector client to create the conversation between the user and the bot. Since these conversations are unique, it is safe to call this even if the bot has already started a conversation with the user. The conversation parameters here are similar to those we used to create the thread in a channel. This time, however, we're defining a conversation between a bot and a single other user, which, when used in the create conversation call, will get us the one-on-one conversation between the user and the bot. With this conversation ID, we now have all the parts of the conversation coordinates, and can send proactive messages. Now we have seen 3 methods for getting the conversation coordinates. 2 of these methods create new conversations, which comes with design considerations. For channels, this involves creating a new thread in one of the channels in a team. This decision point may need to be deferred until a later time, such as when a configuration experience is completed by a user. For Teams users, creating the conversation for each user optimistically can result in the bot making hundreds of conversations when the app is first installed. Now, neither of these 2 paths are optimal, so often apps need to persist more than just the conversation coordinates. Instead of optimistically generating the conversation coordinates, we can instead store the information necessary to create the conversation so that it can be generated in a just-in-time manner. This shouldn't be used as a replacement for the conversation coordinates, however, and the app should make efforts to avoid unnecessary conversation creation. In this table, we can see the minimum data needed to create a conversation in each scenario that would need to be persisted. For a channel, this is the channel's conversation ID and the service URL. For creating a conversation with a user, you need 3 pieces of information: the service URL, the tenant ID, and the user's ID. Now that we've seen the ways that we can get the conversation coordinates, let's move on to sending proactive messages. Mechanically, we've already seen the few lines of code required to send a proactive message, but in practice, challenges arise from the call patterns of proactive messaging scenarios. Often, proactive apps send messages to many coordinates in a narrow window of time. This short burst of high-volume traffic is very different from the more uniform and randomized traffic from conversational bots interacting with users. Like many public APIs, this will result in throttling to ensure quality of service for other users. Throttling for bots follows the convention of using the HTTP 429 status code to indicate the bot is sending too many requests. This throttling will take one of 2 forms: short-term transient throttling or the more long-term circuit breaker style throttling. Many proactive bots want to send these bulk messages as quickly as possible. We recommend designing with the expectation that the bot will experience throttling rather than trying to send slowly enough to avoid it. As a pattern, we recommend persisting these messages on a queue and that bots not attempt to send more than tens or hundreds of messages at the same time. Much like many public APIs, the bot send can be throttled. What makes bot throttling unique is the two-tiered mechanism. The first type of throttling is the short-term throttling. This is very similar to the throttling most APIs exhibit when a service decides its short-term behavior of an app needs to slow down. In this case, some of the messages will be throttled, but not all. We recommend that the bot employ a short wait of a second or two, then attempt to send the message again. Subsequent throttles should wait longer, and we recommend an exponential backoff of 2, 4, and 8 seconds with a randomized jitter of about a second. Many proactive bots can send hundreds to thousands of messages with just the basic exponential backoff and retry and experience no further issues. However, apps that are sending messages to tens of thousands of recipients may encounter a different form of throttling. This long-term throttling can be characterized by the difference in behavior. Even with the backoff and retry, all the messages the bot attempts to send will be throttled. This behavior can be thought of like a circuit breaker. Once tripped, no message will go through. This throttling will last several minutes before allowing the app to send messages again. It is important the bot stop sending messages, as continued traffic will only extend this timeout. After a few minutes, the bot should attempt to send one message to probe if the throttling is still occurring, and only resume sending at full speed once the message successfully sends. So let's look at how we can deal with this in code. Here, we see the implementation of the send with retries function from earlier. This function uses an async policy object from the Poly project. Poly makes handling this complex throttling simple and clear. When we look at how this policy is defined, we see 3 separate policies all chained together. The first, and innermost policy, is the one that handles the short-term transient throttling. It will retry failures up to 3 times, waiting for 2, 4, and finally 8 seconds, plus a short jitter. The second layer is the aptly named circuit breaker policy, which detects when 5 or more messages in a row fail through the first layer due to throttling. Note this would mean that the bot has now attempted to send at least 5 messages 3 times for a total of 15 attempts that have been throttled. This circuit breaker policy will make all subsequent calls fail immediately for the next 10 minutes and make no downstream calls. The last layer is yet another wait and retry policy, but this one has a much longer wait of 10 minutes to match the underlying circuit breaker. When the circuit breaker fails an individual message, it will wait 10 minutes before trying to send the message again up to 5 times, for a total of 50 minutes before giving up on that message. It should be noted that this implementation works well for background services, where holding the message to be sent in memory for multiple minutes is an option. For serverless applications or other scenarios where this block and wait behavior would be expensive or too volatile, we recommend putting the message back on the persistence queue and schedule the next attempt for 10 minutes later. Let's cover some assorted tips and tricks for proactive messaging. First, don't send proactive messages without context. Users should not be confused as to why they're seeing the message. Second, ensure that the outbound activities have the preview text populated. Without this, the toast notifications will appear with generic placeholder text. Third, avoid repeatedly creating connector clients and reuse them as much as possible. Each connector client creates an HTTP connection with Bot Framework and is a common source of memory leaks. Finally, remember to test the corner cases of proactive scenarios. Unlike conversational bots, proactive bots can send messages to locations that don't exist, such as a deleted channel, or to locations that don't accept the message, such as a user who has uninstalled or blocked the bot. All the code demonstrated here today is available on GitHub at akams/teamsproactivesamples. For more information and documentation for the Poly project, which we use to implement the throttling, visit their site at thepolyproject.org. Before I go, I want to point you to a more complete example of proactive messaging. The company Communicator app template is an excellent real-world example of how to architect and implement a proactive bot. It was designed as a way to author and send messages to every user in an organization and is used in production to send messages to tens of thousands of users. It's a full-fledged cloud app built for Microsoft Azure and demonstrates how to use Azure offerings such as Azure Service Bus, Azure Table Storage, and Azure Functions to implement many of the concepts we reviewed here. In conclusion, I highly recommend you check out the code at akms/Teams Company Communicator. Well, that's it for my presentation. Do you have anything else, Adrian?
Nope, that's it. Thanks, Nick.
Thank you. And to everybody out there, stay safe.